We're going to continue our exploration of the concepts of variance and covariance by looking at what happens when we have sums of random variables. Up until now, we looked at the fact that the expectation of a linear transformation of a random variable, because expectation is itself a linear operator, follows a pretty straightforward rule which is summarized in these two expressions, right? The expectation of a linearly transformed random variable carries over this way, and the expectation of a sum of random variables themselves is also additive. Variance behaves differently. There's a square in there. Variance is not a linear operation, and so the expectation of the variance of a linearly transformed random variable is actually insensitive to the shift, but the multiplicative constant comes out squared, and as we saw when we take standard deviations, we end up with an absolute value in there. Now, what happens if we have a sum of random variables? What happens to the variance in this case? So first, let's get a little bit of intuition on the matter by looking just at a really simple case, a uniform distribution over a few variables. In this case, let's think of a die. And so if we have two random variables, x1 and x2, which are the numbers on the two rolls of an unloaded die, then they obviously have the same distribution, x1 and x2, but the distributions of either x1 plus x1 and x1 plus x2 are different, and here we have visualized them in this plot. The yellow histogram is the distribution of 2x1, which is x1 plus x1, and the blue data shows the distribution of x1 plus x2. And it's fairly obvious, and you should convince yourself that these are indeed the histograms you expect to see, that these are different. And that they have different variances, right? These two distributions, the yellow one, 2x1, has a larger variance, has a wider spread than the blue distribution. They do, however, have the same expectation. The expected value in both cases is the same. That should be something that makes sense in your head. If it doesn't, pause the video for a second, take a piece of paper, kind of write it out, and convince yourself that you expect both of these to have the same expectation. But in order to get to sort of confirm mathematically what we're seeing here visually, and here we're illustrating it with only one example, so we want to understand what happens to the variance of a sum of random variables. And so for that, we're going to take and do a little bit of a derivation, which is in your notes. It's in the slides, but I think for these kinds of things, it's useful to sort of work it out together. So, what is the variance of x plus y? Okay, so by definition, it is the expected value of the random variable, in this case x plus y, minus its expectation, right? And it's the expected value of this quantity squared, right? So we're going to introduce a teeny bit of notation in this case, which is that we're going to define mu x as a shorthand for the expectation of y, the mean of y, and mu y as a shorthand for the expectation of y. Okay, this is a square bracket, sorry. And so if we have these definitions, now this becomes the expectation of x minus mu x plus y minus mu y. I'm simply replacing these terms by their definition that I just introduced and expanding out using the linearity of expectation over this term, right? So we have these two, and now let's expand this square right here by thinking of it as the square of two terms. I'm going to keep these puppies together. So this is going to be the expectation of the square of the first term, x minus mu x squared, plus twice their product, x minus mu x times y minus mu y, plus the square of the second, y minus mu y squared. So this is what that term looks like. Now I can use the linearity of expectation to collect. This is expectation of x minus mu x quantity squared, plus, let me write this one right here second, and let's leave this one third. So I'm kind of reordering this expression, plus the expectation of y minus mu y squared, plus twice the expectation of x minus mu x, y minus mu y. Okay. So now let's think back about our definitions. What do these two terms look like? Expectation of a random variable minus its mean, minus its expected value squared, right? The expected value of the squared deviation from the mean. This is exactly what we have defined as the variance, right? This is exactly, so we're looking at the variance var of x plus y. This is the variance of x, and this is the variance of y. So we have that the variance of x plus y is equal to the variance of x plus the variance of y plus twice this quantity, the expected value of x minus mu x times y minus mu y. It is a quantity, so as we see, the variance of a sum is the sum of the variances plus some other thing, plus twice this other term. Now this term has a structure similar to the definition of variance, right? It is the expected value of deviations from the mean, but in this case of the combination of x and y. It's not of x squared or y squared, it's of their combined product. And this quantity is defined as the covariance of x and y. So we arrive, this is the definition of covariance, we arrive at our final definition, at our final expression, which tells us that the variance of x plus y, of the sum of two random variables, is equal to the variance of the first plus the variance of the second plus twice their covariance. Okay? And let me go back to our slides. And so this is the expression, this is the little derivation that we have there, and in here we have defined the covariance as this quantity that was in the iPad derivation. So as you can see, the variant with this definition of covariance, it's actually a more generic definition because it encompasses two variables. Then we can say, we can observe that the variance of one variable is actually its covariance with itself, right? And a calculation that we will not repeat here, but that uses these exact same tricks that we've been seeing, shows you quickly that the covariance of two random variables is equal to the expectation of their product minus the product of their expectations. And so we now have this, this general form, this general expression right here that tells us how the variance breaks down into the sum of variances plus the covariance, right? Written out here with our covariance notation. And now we can ask the question, when is variance additive, right? When is the variance of the sum of two random variables equal to the sum of the variances? Well, for that to be true, this would have to be 0, right? So when is it the case that two variables have 0 covariance? Well, a sufficient condition is if they are independent. If knowing the value of, if knowing the distribution of x tells you nothing about the values that y can take, these two are independent and their covariance is 0. Now the converse is not true. The converse is not necessarily true. Independence is a very strong condition, and it implies 0 covariance. So this is known often as the addition rule for variance that says the variance of the sum of two random variables is additive if they are independent. As we said, this is not an if and only if, right? There are cases where you can find 0 covariance because of the properties of the distributions, even though they are not independent. Now, the units of covariance are hard to interpret, right? We're talking about a quantity which is constructed. Let's go back to its definition here. The covariance is constructed as an expectation of the product. So if you have two quantities that have different units, the covariance is going to have as its units the product of those two. Let's say that you were looking at heights and weights, for example. The covariance between height and weight is going to have units of inch-pounds if you were measuring height in inches and weight in pounds in US units, or imperial as they used to be known. that is not a unit that is particularly interpretable. So one way to get rid of that is to scale it. And so we introduce a concept known as the correlation, which is just by definition taking the covariance and rescaling it by the standard deviation of each variable. So if we look at what happens in here, quickly you can see by using again the properties of expectation, you can see, remember at the end of the previous lecture, we looked at what is the standardization of a random variable when we convert our random variables into these centered standard deviation 1, variance 1, unitless variables. Well, this is exactly what this construction gives us. This scaling of the covariance by the standard deviation is exactly computing the expectation of the product of the two variables, but after having been standardized. So, and this is known as the correlation. So this scaled covariance that can be computed by using the standardized version of the random variables is known as the correlation. It's unitless, so it is much easier to interpret. And its numerical range is going to be always between -1 and 1, because it is based on variables that can only once they've been standardized, they always range between 0 and 1. So this correlation has a well-bounded numerical range and is unitless. So it is much easier to interpret. We had seen in data 8 correlation between samples, between two lists of numbers, right? That is known as the sample correlation. This is now the definition, that same definition, but generalizing it from a single sample, from a single list of numbers, to the notion of a random variable that has an underlying distribution. But it is basically the same idea that you're already used to from data 8. So what does it mean for two random variables then to be uncorrelated, right? So if this is our definition of correlation, two random variables are said to be uncorrelated when their covariance, or equivalently, their correlation is equal to 0. And independent random variables are uncorrelated, but as we said, the converse is not automatically true. Not all uncorrelated random variables are independent. Think, for example, of x being the uniform distribution on the set of either -1 or 1 outputs. So it's a binary random variables whose only outputs are -1 and 1. You should be able to convince yourself, and if it doesn't click, grab a piece of paper, stop the video, and work it through. That x and x squared, the random variables x and x squared, are fully uncorrelated. You can compute their correlation. They are, given that it's such a simple distribution, it's a very straightforward calculation, and you'll find that they're uncorrelated. However, they're obviously dependent. Once you know x squared, right? By definition, x squared is going to be 1 regardless of the value of x. And so these are not independent variables, but they have 0 correlation.